What's happening, folks? Geologist Philip Prince in the Western Pacific Ocean today, talking about the Marianas Trench and specifically the Challenger Deep of the Marianas Trench. Deepest point anywhere in the Earth's oceans, almost 7 miles below sea level. Want to talk about the geology of this. Why is this such a deep spot? Got plenty of cool diagrams that go along with this. I really like this story because it's really fundamental to understanding some big ideas of just how the planet at large functions. A system like this also has a lot of interesting connections to things beyond ocean depth, one of which actually is how global climate functions. So, really cool place to talk about, really interesting place to look at if you can find it. Not really any land nearby. Throw out a few reference points there. It is very much out in the middle of the ocean, and there's a good reason for that. Parts of the ocean that are going to be really deep probably not going to have a lot of dry land associated with them because the Earth's crust is going to be down below sea level there to begin with. Now, there is land near the Challenger Deep. There's land above the Marianas Trench, Guam, pretty well-known island, certainly here in the U.S., of course. Tinian and Saipan were very significant places during the Second World War. Several other islands extend up in that crescent-shaped arc going up towards the top of the screen, and a lot of them are really interesting to look at on Google Earth. The arrow there is pointing at Pogun Island, and if you look at that on Google Earth, it is like the iconic volcanic island in the ocean. It looks like a movie set or something like that. Sort of a round island, big volcano right in the middle of it. You see the nice crater there. This erupted in 1981. That's the lava flows that you're seeing there, I think. This is sort of what you're going to see in terms of land masses associated with a setting like this. Again, because the details of the Earth's crust and how the plates are moving are such that it's very difficult to make land stick up above the surface of the ocean. In this case, there's a lot of heat here because this is a volcanic center. There's actually addition of material to the crust. Combine that with the heat, yeah, you can get some limited dry land on an island like this, but if you turn off that heat and you turn off that magma or erupting lava, this thing is going to erode away in no time. Now, in terms of what is under a location like this is what we're going to be thinking about here. That's going to be the Marianas Trench as portrayed. Of course, if you clicked on this thumbnail, you might have seen it and said, well, the Challenger Deep is deeper than 30,000 feet. Yes, that is the case. I drew this little cutaway actually away from the Challenger Deep just a little bit. Other things fall a little bit short. The oceanic crust there would be about 5 miles, 8 kilometers, maybe even a little bit thinner than that. The lithosphere beneath that, which is part of the Earth's mantle, but it's sort of connected and moves with the crust. Crust and lithosphere are what make up the Earth's moving tectonic plates. Be about 70 miles thick, give or take. Underneath that is asthenosphere. This is still part of the Earth's mantle, and it's solid, but it's a plastic kind of pliable solid. Why is the mantle green in my videos? Talk about another one. If you could see rocks of the Earth's mantle on Earth's surface, they'd be green. They'd have to be cool enough for you to hold them. You see them at the Earth's surface occasionally, very rarely, because they're too dense to be up there. Now, if you took them immediately from the mantle at their mantle temperature and brought them to the Earth's surface, they would glow very brightly, but they'd also melt because they don't have tremendous pressure preventing them from melting. I don't like to draw the mantle as this kind of bright orange thing or whatever because it suggests that the whole thing is molten, which is most certainly not the case. There is a little tiny bit of melt associated with the asthenosphere, but fundamentally it is a solid, and it is again like a plastic pliable solid. Now, down there at the very bottom of the image, about 415 miles deep, 660, 670 kilometers. Lithosphere is going down and kind of flattening out down there. Again, this is not the scale, but this is representing just how deep this lithosphere might be able to go down into the asthenosphere before it doesn't want to go any further down there, right? And so what am I talking about there? That's implying movement. And yes, movement is very much key to understanding this system. So we'll be getting to that with a diagram animation momentarily. Thinking about the overall scale of things first, if you're trying to draw or diagram this, It's not that deep. The Marianas Trench is the deepest point anywhere on Earth. That line is 125 miles long, 7 miles deep on that end, 3.5 miles deep on that end, just a little bit over a mile deep on that northwest end above a seamount. If you drew this out in a profile, the trench is not going to be that dramatic. Yes, it's the deepest spot anywhere in Earth's oceans, but it's not some vertical chasm or something like that, as you so often see it portrayed, right? So why is it there? What's the main geologic cause? And fundamentally, it's because one plate, the Pacific plate, sort of diagonally lower right on this screen, is sinking under the plate diagonally at upper left. Now, it could be called the Philippine Sea Plate. Some people recognize a Marianas microplate, but one way or another, that dark trench line there is the dividing line between the sinking plate and the overriding plate. And that sinking concept is really critical here, right? Why is it sinking? It's very dense. Why is it dense? It is old. Oceanic lithosphere forms at mid-ocean ridges or spreading centers where molten rock rises up, cools, and kind of pushes away as more and more material fills in there. The further you move away from those mid-ocean ridges or spreading centers, things start to cool down, and as they cool down, they become more dense. The Pacific plate here is about 180 million years old. That's pretty old for oceanic lithosphere to still be up at the surface of the Earth, right? It's ready to sink at that point due to its density, and that's absolutely what's going on here, right? So sinking is key, and we call a feature like this in geology a subduction zone. So if you call something a subduction zone in a geologist's mind, is going to be something like you see here. Now, this is a simple diagram. The dark line there is representing crust and or lithosphere, kind of both. It's not drawn to scale, but it's intended to show that sinking process, right? And associated with that sinking process is lateral movement across the planet's surface, and also the development of melts above that sinking slab of lithosphere. Right now, what's melting there? Not the sinking part. It's actually the rocks in the Earth's mantle above the sinking part. The sinking part is taking all sorts of stuff down there into the Earth's mantle with it. It was interacting with the oceans, the hydrosphere, which are interacting with the atmosphere. So it's taking water, all sorts of volatile things down there and putting them back in the mantle. As that sinking slab heats up, those compounds come out of the minerals, out of the sediments, and they react with the mantle and cause it to melt just a little bit. And that's actually where the erupting stuff in the islands comes from, right? So that's where the whole climate story comes in. The sinking lithosphere and crust specifically, because that's the top part of it, that's taking stuff from the oceans and atmosphere, putting it back in the earth over big time scales, and then stuff is coming back into the oceans and atmosphere out of the volcanoes, right? So there's this really interesting kind of recycling interplay going on in association with this system. And this is what makes the trench, right? It's that sinking where that plate is sinking down and actually bending down. So that physical downward bend is what makes the trench. And it's sort of like a flexure, right? That's what talking about it not being like some crazy chasm like that or something. It's related to the flexure or the bend there, right? It goes down as far as it can sink for density reasons, which would be like the dashed line there. That's at 415 mile, 660 kilometer depth. And then at that point, sort of who knows. So you got various potential movement aspects associated with this sinking process. One that's shown here is this concept of rollback, where the sinking slab kind of settles or collapses backwards as shown there, and that actually produces like a tractional force on the overriding plate and starts to pull it away potentially from the rest of the plate, or it can sort of pull that whole plate with it, right? So that is one interesting detail of the movement. And honestly, if you put it all together, you might have sort of both of those acting as one, right? But the driver again for the motion there is this sinking process. Now, on top of that sinking process and taking material from the oceans and atmosphere, putting it back in the earth over huge time scales, and then material comes back into the atmosphere as a result. There's also a lot of turbulence and kind of stirring up of that plastic asthenosphere rock. Um, so so there's a lot of movement going on here, and for this subduction or sinking process to continue, uh, that asthenosphere has to be able to move and sort of, if you will, kind of fill in the space that is produced by that sinking slab. So there's a lot of really just fascinating, massive, large scale movement going on here. In the description, there's going to be some links to some physical models that show this process on YouTube. I would highly encourage you to watch those after looking at these diagrams and see what you think of them, because they really bring this to life. Incredibly interesting to look at. I don't know what materials they're using. It's something with very subtle density contrasts, but it does a very nice job of illustrating this point, right? So that sinking process that's what we're illustrating in the thumbnail in this kind of conceptual model, right? So that's what's going on. But what else is contributing to this incredible depth, right? So we got the sinking sets the stage for it. Any kind of subduction zone, you're going to have a lot of depth there. Another big part, there's no source of sediment to fill in the trench and make it less deep. There's not a landmass around there to provide it. Little Guam there, not quite going to cut it. If you were to compare this to another ocean trench with a big landmass nearby, the Nankai Prism and Associated Trench that's just south of Japan, there's a nice example. It's actually still the Philippine Sea plate that is going down underneath the Japanese island arc there. Huge inputs of sediment. They pile up on top of that plate, and they actually end up getting scraped off of that plate as it goes down under the Japanese arc there, kind of like a snowplow. And you can actually see all these interesting little wrinkles where that sediment is getting scraped up. They're not little, the scale of miles of thickness, but suffice it to say, having this big sediment source, this big landmass, that's altering the potential depth of this trench. Now, a lot of other factors go into trench depth unrelated to sediment source. How old and cold is the lithosphere? Things like that. That's not the only control, but in the case of the Marianas Trench, there is absolutely no sediment source. And when you compare it to one like this, where there is a big sediment source, it's a pretty significant difference, right? So sinking, old, cold lithosphere, no sediment to fill it in. What's going to take it over the top, right? A lot of these geologic superlatives, there's always something that is just that cherry on top, right? That makes it really exceptional, like nothing else. And in this case, it's actually going to have to do with that sinking lithosphere, that sinking slab. Interesting to look at questions like this and sort of see how they're portrayed in the scientific literature. I've been around geology quite a while. You hear this discussed time and again, and there are certain concepts that always come along with it. The big ones in this case are the age of the lithosphere and the lack of sediment, and the fact that, as you see here, it's kind of like really sinking down there steeply. But you got to have something else mixed in there. Two papers that you find online do a very nice job of communicating and illustrating this. Gewurtzman and Stern, Bob Stern there, I think University of Dallas is a name that you see connected to a lot of Marianas Trench research. I think there's some interesting National Geographic stuff he's contributed to. Millerdow, 2006, also does a nice job with this, and they are particularly focused on a specific detail of this sinking part that's right underneath the Challenger Deep that sets it apart just a little bit from the rest of the Marianas Trench, right? So to bring this one home, going to have to jump out to paint and actually sketch it out, all right? So hang on just a minute. All right, here we are in paint like usual. So this is an interesting diagram to try to put together because we're going to do some similar cutaway thing to what we started out there with in the thumbnail image. Just kind of block in our cutaway of the earth. All right, and we'll do a little bit more narrow of a line there. So that's going to be our cross section down down through the earth. The reason I make the mantle green is that the Earth's mantles rocks. If you ever see them at the surface, they're green. Talked about that in another video. You don't see them that much because they're too dense to be up there in most cases. But if you could get them there, and had them nice and cool, hold in your hand, they would be some shade of green, right? So that's why we're always doing that. Okay, so we're gonna put an ocean surface on top of this now. All right, adjust that just a little bit, right on. Okay, very good. And now we'll need to get in here and draw in our crust slash lithosphere. Probably not going to go to real extreme detail with this. Suffice it to say, we are representing that upper, more brittle part of the planet, the one that makes up the mobile tectonic plates, and of course, the one that is actually involved in the sinking process here that is producing the Marianas Trench and the Challenger Deep. Okay, so there's overriding plate. Have our sinking one coming in here. All right, and that's about all of it I'm actually going to draw right there. That's a little bit too thick compared to the neighbors. We'll fix that up here just a little bit. And there's a reason for this, because this kind of speaks to why in the world is this the absolute deepest place anywhere on Earth. The consensus that you read is that the sinking plate, the sinking slab, as it's typically referred to, is sort of broken in the vicinity of the Challenger Deep. So there would be a part broken off like that, and it would be separate from the rest of it that would go down something like, you see drawn right there, like was portrayed in the thumbnail image for the video. No one has been down there to look at this. You can't go down there to look at this. It's a 100 plus, 65, 70, 80 miles under the earth, something like that. But much like the seismic reflection talked about in other videos on this page, people can assess how energy waves travel through the earth, and they interact differently with different materials down under the surface, and it's possible to get that kind of sonogram effect of what's down inside the earth. And whether or not there is a sinking slab present at a given location is absolutely something you can see. And underneath the Challenger Deep there isn't one, right? So we'll kind of keep tweaking on this here. I need to accentuate my trench there just a little bit and have that looking better. So we'll try to tidy that up. The interesting thing about sketching all this out is it's just like if you actually do it to scale, the crust is impossibly thin. I mean, it's like an apple peel or something like that, and even the lithosphere is pretty thin. Now, if we drew lithosphere in here, it would be thicker than the black area as it's drawn. But we'll fill in some water on top of that crust now and try to keep this whole thing moving here. Let's see, we'll give it a little bit darker color to imply depth. There's that. There's the trench, which at 7 miles deep again is just not that big of a deal, to say the least, in terms of the overall scale of the planet. Now, what is interesting is that 7 mile depth is deeper than the thickness of the oceanic crustal rocks, but it is not even close to the thickness of the lithospheric rocks. Okay, so getting that put together, that's where the trench is going to be, is kind of down in that area. Okay, so there's going to be our trench. Here is the torn off piece of the sinking slab there. And then the rest of the slab over here is actually continuous, supposedly all the way down to that 415-mile depth, that 660 or 670 kilometer depth down below the surface there. And the way I read it, I miss a lot with structural geology. I am not exactly total expert in these aspects of geodynamics, but the way you read it, the fact that that is like continuous all the way down to where it's flattening out, is almost like you might imagine trying to, I don't know, like a piece of bending foam or something like that. You're pushing down and it's pushing back on you a little bit, something like that, where the connection with that kind of fixed greater depth down there is causing forces onto the sinking slab. One way or another, you get the tear here. Uh, you got this thing kind of sitting down in the earth back here, and that would be, cut off against the side of the sketch over there. So there's your sunken slab, and your little islands up here. We'll make them a little bit darker green of a color. They would be sitting something like back from the trench a little bit, making this kind of crescent shape going off to the north. We're trying to look here in parallel to the deepest part of the trench. Maybe we need a little eruptive activity on that one right there. It's a good thing to do. Okay. Nothing too bad. They got everybody out of there in time. So that distinction right there, that little torn off piece that is sort of able to basically just go straight down, is what is making that particular part of the trench just a little bit deeper than the rest of it. So it's an interesting distinction. Again, it's all based on movement, and it's something that, like I said earlier, like we can't go down there. You can't drill to that or anything. You're reliant totally on these remote sensing techniques. But in terms of thinking about how the Earth works and how the Earth is very much a mobile thing, the part of the Earth we deal with, the uppermost part of the crust, is so tiny in comparison to the overall scale of things that sometimes you lose a sense of how it's just this overall moving system with sort of logical connections between things. So I don't know, we can kind of finish up here. We'll run the trench out as if you were able to look down underneath the ocean here. The trench would be kind of going out there, something like that. Okay, so there's our conceptual diagram of what's going on under the Marianas Trench. So in summary, it's always going to be deep because it's an oceanic trench. Oceanic crust and lithosphere don't really make land to begin with for density reasons. You get one half of that system sinking, and not only will you not have land, you're going to have a very deep spot where that downward bend is occurring. If you make sure there's no sediment to go in it, it's going to stay that much deeper. And you throw in some particular little detail, like this torn off little scrap of slab there that has nothing sort of holding it up and it can just sink straight away, then you're going to end up with one of these global superlatives, nothing else deeper than it, at least right now. Has there been something deeper in the past? Would there be something deeper in the geologic future? Very likely so. But that is the main thought on what is controlling this right now. And a final thing to keep in mind here, since we're still talking about it, we'll kind of block this out. Find the right color there. Something else that you read about when you look at studies of this type of a system, two interesting details that are kind of flow related, right? One is that the end of that slab has like almost like a pointed shape, which is thought to allow it, almost like the prow of a ship or something, I guess, like to kind of cut through that ductile asthenosphere. And secondly, because you have all this gap down here under this torn off area, that's allowing that material to kind of flow and circulate very freely. So there is less impediment, if you will, to the sinking of the lithosphere in this location. So really cool to think about. There are, I guess, other comparably deep places like the Puerto Rico Trench is about 28,000 feet deep. That's in the Atlantic. That's not even quite a subduction zone yet. So that's another one to think about. There are lots of active subduction zones that are not as deep as the Puerto Rico Trench. I don't know how they all stack up globally, but the common thread between them, all of them without exception, is that sinking process, like that downward bend, and you can just kind of build up your explanation from there. So definitely check this one out on Google Earth. If you scroll around in Google Earth, it'll tell you water depths. You can Google search for Challenger Deep. It'll take you right to the spot. And you can also check out all the little land masses around there. It's kind of interesting to think about being on this tiny little island, and not only are you in the middle of the ocean, you're right next to like the deepest spot there is. So very, very different from where I'm coming at you from here on the East Coast. Hope you enjoyed this. Check it all out on Google Earth, and we'll see you next time.